Hello. Hi everyone, can you hear me now? I think I changed a few of my settings. Thanks, Tim. Yeah. In case if it's dropped, please let me know. I will fix it as early as possible. I'll keep an eye on that. Thanks, everyone. Hope there is no background noise. If there is any background noise, please let me know. I'll change my settings. Cool. Let's get started. I think before talking about this session, let's do a quick 5 minutes review on the last session so that helps to follow on. I think in the last session, what we did is we did few things. So one is we trained a PET classifier, which is like a fine grained. So what does it mean is normally in PET classifications, you classify like there is static, but not too bad. Okay, maybe I'll have a look next time, but I'm going to keep these settings for now and to see. Let's see how it goes. Thanks, Annie. So what does it mean fine grained? So in fine grained, instead of just predicting cat versus dog, you try to predict so many variations of the cat, I mean different breed, and you also do the same thing with dog. So it's very challenging compared to only dog versus cat. So if it's dog versus cat, it's easy because there are some distinguishable features, but in fine grained, most of the cat look very similar. Even though they are different breed, it's very hard to distinguish. So it's very challenging. And to do this modeling, we were using different models. I think we explored few of the Fastai models as well as some of the new models from TIM library. So especially, I think in the last session we used connext based models. We got like 5% improvement when compared to normal ResNet versus connext. I think that's a good move. Then we try to understand neural networks. So in neural networks, we have input and output. Then we randomly initialize weights and biases. So they are like random numbers in the beginning. Then during model training, they will update itself based on the loss. It calculates the loss, then it will try to change weights and biases a little bit to see if the loss goes up or low. Then to do that, it will be using like back propagation, which is just a finding derivative of the loss with respect to weights and biases. So to do some simple back propagation or taking a derivative, it's easy because in this equation we have only one input and one output, and we know that the output looks like y equal to mx. Then we can take a derivative. So in this case, our prediction is x multiplied by w, which is like initially they are the random numbers, random w. Then we calculate the loss. Our loss will be calculated by mean square error. So this is square error. So in square error, y prediction is like xw. Then we have y, which is the output label. Then we square that. So let's do some expandation. So if you expand, you will get x square w square minus 2x wy plus y square. Then if you take derivative with respect to w, you will get 2x square w minus 2xy. Then this is the this is your derivative of this equation. Cool. Then based on that, you update your weights and biases during the training. So initially the weights and biases are random numbers. Then during training, it will update itself based on the loss. Then at the end, your numbers will be very meaningful. So to understand this, we were using very simple data set like hours spent and grade, but the same concept applies for even problems like solving images, like image classification, image regression, and sound and text, videos. If you are doing any problem, so we will use the same concept. The concept is the same, but for simple equations like that, we can make derivatives ourselves. But if the problem is too huge, we cannot manually do the calculations. So that's why we are using libraries like TensorFlow or PyTorch. So they do the derivative for you. Okay. I think with this background, let's move to the today's session. In today's session, we will have two big areas to cover. So one is Huggingface NLP classification model, and then another is lots of small concepts like what is fine-tuning and what is ULMFit, what's the difference between overfitting and underfitting and how to identify those, then what are training, validation and test splits, then what's the difference between metric and losses, then understanding Pearson correlations, then clipping. Okay, so we'll cover all these things in today's session. I think maybe I'll start with fine-tuning. So we'll learn few concepts as well as some programming. And for programming, what we are going to do is we will be using Kaggle this time. So in the previous sessions, we were using Google Colab, and I was using some Vertex AI for a few sessions. But in today's session, we'll get some practice on Kaggle notebooks. So Kaggle is like a competition website. You can see it here. So if you are a beginner, let me introduce like 1 or 2 minutes on this. So in Kaggle, you can see a few things. One is competitions. When you click competitions, you can see what are some of the active competitions and past competitions. I think it's loading. Let me refresh. Cool. You can see some of the active competitions and past competitions. So there are so many competitions going on here, and it's useful. And you can also do some filtering to find the competitions you are interested in. Then the second thing is datasets. I hope the streaming is fine. Maybe my Chrome. Okay, so in datasets, you can see a lot of different datasets that you can use for your machine learning or deep learning projects. You can also see popular datasets. Then here are some of the recently viewed datasets of mine. Then it has lots of different genres. You can find the genre you are interested in, and you can download some dataset and you can start working on that. Then there is code. So in code, you can see how other people approach solving some challenges or knowledge sharing, something like that. And you can see the upvote, so which means 21 people liked this work. And it also has lots of different categories. You can also do some filterings to see if you are interested in Python or other things. Then it also has some courses. They are very interactive. I think my Kaggle is slow today, not sure. Yeah, here you can see lots of different courses. on different topics. Cool. And Kaggle also provide free GPUs, so that's quite useful. And for today's session, we'll be following this notebook, Getting Started with NLP for Absolute Beginners. So this was written by Jeremy Howard for his lesson 4 that we are covering today. So to use this notebook, what you can do is you can do two things. One is you can quickly read all these things. Otherwise, you can click copy and edit. If you click copy and edit, it will open a new interactive notebook for you, where you can run every cell and then you can see the results by yourself. And you can also save version, you can do some modifications. It's good for learning. Once you click copy and edit, you can see this screen. Here you can also see my GPU and other information. It says my GPU is on, and the size, you can see it here. Then the RAM, 13 GB RAM, then GPU usage, GPU memory usage. You can see all these things here. Cool. And another thing to note here is there is settings. You can choose accelerator. Sometimes if it's CPU, just change it to GPU. Okay. Also, sometimes you need internet to install some libraries. If internet on is turned off, just click turned on. Okay, turn on this. Okay. Cool. Oh, sorry about that. Okay. So the other things are very similar. You can create lots of different code, and you can also create markdown. To run this, you can click this button. So when I click shift enter, it runs. I'm going to show you this. Shift enter. Here you can see the GPU that they have allocated to me. They have allocated P100 GPUs, which is quite good. And it's very similar to Google Colab and other Jupyter notebooks. Also, once it's done, you can save your version. And also you can share your work with others. So especially if you're a student and looking for a job, so it's good to participate on Kaggle notebooks and competitions, and you can share your work with others. Cool. Okay, now let's move to concepts. First of all, let's try to understand what is fine tuning and what is pre-trained model. So let's say you have got very few data sets. Like let's say you have you want to predict cat versus dog, and you have got only 100 images each. So this is your problem. So this is the problem you are trying to solve. You have got only 100 images of each cat and dog, and you are trying to build a classification model. Let's say the model you are using is maybe ResNet 34, and this ResNet 34 has 34 different layers. So initially this is your input, and it passes to a layer. Then finally, let's say this is 34, and finally you will have a final layer with two output. One for cat and another for dog. So they are like logits. So think of it, it's like a probability value. Logits means it's not exactly probability value, but let's assume there are some numbers, and let's say the numbers are 2.3 minus 1.8. In this case, you will assign the maximum, which is cat. Okay. Cool. let's say this is the model you're trying to use. The problem here is you have got only 100 images of each, and you need to learn so much for this model because there are 34 different layers, and each layer has so many different neurons. You need to learn so many weights and biases. So sometimes, in most cases, it's very hard to learn with less dataset. So what you usually do is, there is another dataset called ImageNet. So this ImageNet has millions of images, and it has two versions. One version is 1000 output, 1000 classes, and another version is 22,000 classes. Okay, so let's talk about 1000 classes. Out of 1000 classes, you will have images similar to cat. You will have images similar to some animals, and you will have lots of different objects, etc. Okay, so let's say you are training a model. Let's say someone already trained a model and they exported their model's weights. So which means all the numbers here, they are very meaningful at predicting something, so they are not random. Then what you can do is, you can use this pre-trained weights. You can put this pre-trained weights to your model weights. So these numbers are very meaningful numbers. And this ResNet in ImageNet, it has 1000 different values, but we don't want 1000 different outputs. We just want only 2 because our problem is cat and dog. So we replace the last layer and we replace that with 2 different output, cat and dog. Okay, 2 units. Cool. I'm going to show you why this is useful. If you see this one, this comes from Zeeler and Fergus paper. If you see this, let's say there are 34 different layers. The initial layers, you can see my mouse movement. So initial layers, they are good at predicting some patterns like color gradients or diagonal and horizontal edges, vertical edges, those kind of things. You can see it here. And the second layer might be good at predicting some combinations of both, like some shapes, like curves, circles, something like diagonal and corners. So it's good at predicting those things. And maybe the final layer, they are very good at predicting the task at hand, like whether this image is dog or not, those kind of things. So when you use pre-trained weights, already these weights are very meaningful. You no need to change too much. What we can do is, we can use these weights to learn only the final layer, which is cat or dog in our case. So that's all about pre-trained model. In pre-trained model means you will use some weights and biases that was trained by some other person in some other data set. Okay, so that's all about pre-trained. Now let's talk about fine-tuning. So pre-trained means, for simplicity, I'm going to call this as ImageNet, weights and biases. Then fine-tuning means, so in fine-tuning, you remove the loss layer, because in ImageNet, the loss layer has 1000 different output. You remove that and you attach 2 output for our problem. Okay, cat and dog. Then you change only the last few layers, the last layer. You no need to change the initial layers, because the initial layers are already good at predicting some shapes. We don't want to change that too much. We can just change the last layer. So that process is called fine-tuning. So I think whatever I have taught you, I used image versions. But now let's see how fine tuning applies to text. So in text, in language models, what we do is, maybe let me write here. So let's say there is a sentence like, I like this movie, and this is positive sentiment. Let's say to make this prediction, what we do is we build a model, and the model is like a mathematical calculations. We just multiply lots of numbers. So we need to convert this to a number. So what we do is we create a random vector for each word, and let's say the numbers are like 0.3, minus 2.3, 4.8, and like this. Similarly, you have different random numbers. Then in the language model, what we do is you take one word and you try to predict the next word. So likewise, you build a language model. While trying to predict the next word, you will update all your embedding weights. So this random number, we call this is embeddings. So embeddings means a vector that has some numbers like this. So initially it's very random, and during training it will update itself, and then those numbers will be meaningful at the end. Okay, so let's say you are trying to do something like some scientific journal classification model, something like that. To do that model, instead of building a language model on your dataset, what you can do is you can download some dataset like Wikitext 103. Then you use that dataset to build a language model. If you are using that language model, those random embeddings are trained using the Wikitext. Then after that, you can use your own language model, I mean the task at hand. In this case, that problem is IMDb classification. Here you will use IMDb classification dataset to fine-tune your language model. Then you use that language model to do some classification. Okay, here you can see the fine-tuning happens like this. So in comparing to computer vision, think this Wikitext as ImageNet dataset, and this is your cat versus dog. Cool. I think this approach is called this approach was explained in ULMFit paper. Cool. Now let's get started with Huggingface NLP classification model. While doing that, we will cover these things like how to fine-tune a pre-trained model, and we will understand different preprocessing techniques and how to train a neural network. And while doing that, we will understand the concept of overfitting, underfitting, what's the difference between training, validation, and test datasets, then different metrics, Pearson correlations, and clipping. Cool, let's do that. Okay. So first of all, let's get started from here. So here Jeremy talked about different problems you can solve with NLP, like sentiment analysis, author identification, and legal discovery, organizing documents by topic, and training inbound emails, and there are many more. So the problem we are trying to solve is, maybe I'll show you this. Okay, US patent phrase-to-phrase matching. Let's see some data and try to understand the problem first, and then we can use NLP approach to solve that. Let's click train dataset. Okay, so this has a few things. So this is abatement. So this is a word, and this is another word like anchor, target, and context. Think context is like a category, and then we are trying to predict the score. If both are very similar means, if both are same means the score should be 1, and if they are similar means 0.75, and if they are two different things means 0. Okay, so here abatement and abating, they are same, so it's 1, and here abatement and central hub, they are totally different, 0, and abatement and deficiency, there is some similar, so it's 0.25. So this is the one you are trying to predict, this score. Okay, so first of all, to download dataset, you need to set these credentials. Due to privacy, I removed my credentials. So how to find that? Find your credentials is just go to Kaggle and click your profile, and you can see the settings. In settings, there is a tab called credentials. Click that, and it will download a JSON file. If you open that JSON file, it has your username and key. Just copy this and paste it here. Okay, paste it here, and username is your username and key is the key you can see on the JSON file. It should be the same format, JSON format. Then after this you can do shift enter, then you can download datasets. Okay, here we are just making a copy on our local drive, so that's what going on here. Cool. Then what we are trying to do is we are setting this as path. Path is US pattern phrase to phrase matching. If you go to the competition, let me go. Okay. I think my Chrome is super slow. Cool. So I'm trying to open the competition page, and if you see this, it has US pattern phrase to phrase matching. You need to copy this exactly the same. Just copy this and you can paste it here. Then it will download the dataset using Kaggle API. Since it knows your username and key, it will download automatically. And also before that, you need to go to the competition page and click the data tab, and it will ask you to agree that for the terms and conditions. Okay. Also, you can see the score meanings here. One is very close match, 0.75 close synonym, and 0.5 synonyms which don't have the same meaning, and 0.25 somewhat related. 0 means unrelated. Okay, this is the 5 different output we are trying to do. Cool. So this is a Jupyter notebook trick. You can use exclamation, and then you can run any kernel commands, and also you can pass some Python variable names like this, curly braces, and you can pass something. Also, you can do the same thing in if else. I think here Jeremy used conditionals to do something. So it's only applicable to Jupyter notebooks. Cool. Then we are importing standard libraries, then loading the dataset. So this is the dataset. You can see it has some ID, then anchor, target, some context, and you are trying to predict this one. And you can see how many unique things are there. Count, there are 36,473 unique data points, and in anchor it has 733 unique, and target 29,000 unique, and context 106 unique. Cool. I think in this competition Jeremy tried a few things, and he found that the best way to do that, I think one of the best way to do this is converting both anchor and target and context as a single input like this. So he tried to combine everything, and he uses something like text1, text2, and anchor to combine things, so that the model, if the neural network sees this, it will assign less weights to text1, and it knows after text1 it's like some in this case context, then text after text2 it's like target, then it also has some anchor. You can see the anchor is the original word. Okay, I think our dataset is ready. Now the step we are trying to do is, let me show you. Okay, so in deep learning, even though you are doing some text or image or audio or video, you need to convert the data to numbers. So data to numbers, then you can apply the numbers as an input to neural network, then you will get output numbers. Okay, so images, if you are using image, the images is like, it has height and width, and it also has 3 different channels. One channel is for red, green, blue. So there are 3 channels. So each pixel has its own number. So even though it's an image, it's like a tensor of lots of different numbers. Similarly, to convert text to numbers, we need to do some pre-processing steps. So let's say for simplicity, I'm going to assume the text is, I like this movie. So this is a sentence, and let's say the output is 1, which means this is a positive sentiment. So this is our sentence. We need to do a few pre-processing. One of the pre-processing is tokenization. Tokenization means just convert this to, split that into word. Okay, there are 4 tokens. I like this movie. Okay, I like this movie. Then you can convert each unique word and create embeddings. So initially those embeddings are random numbers, but if you are using a pre-trained neural network, pre-trained model, these embeddings are not random numbers. They are trained from some other different related datasets. Okay, let's check this. Okay, go to Kaggle, click on the box. Okay, thanks team. Cool. Okay, so in pre-trained model, those embeddings are coming from different datasets, different models. So these are the 2 steps we usually do for deep learning. Like you convert everything to tokenization, and then after converting everything to tokens, you try to numericalize that. Okay, Those are the two steps. But previously, before deep learning, some of the pre-processing things we usually do for text is, okay. I can recall a few things. One is you lower all the text, then you remove punctuations, then you remove stop words. So stop words means removing and, or the, and, etc. That does not contribute a lot to the model. Stop words. Then I think we do tokenization. Then you do stemming, lemmatization. So this stemming and lemmatization is a way to get the root word from any word. So processes, I think my pen taking some time to write. Let me write, it will appear. Processing becomes process. Cool. I think it's taking some time to write, but let me continue with the code for now. Okay, I think our dataset is ready. Now we are going to use Huggingface datasets and convert that to dataset, and you can see it here. Dataset is created from dataset from pandas. Then you can pass this df, and your dataset has a few things. I think it's loading. We can focus on this. Cool. Datasets. The dataset is very similar to data block in what we have seen in Fastai. And one more thing I would like to recall is in today's session we are covering mostly on Huggingface, not on Fastai, because this lesson focus more on Huggingface. So Huggingface is a library. Transformers is a library from Huggingface, and here you can see it has lots of models, datasets, and spaces. Spaces means you can upload your own apps like Gradio or Streamlit apps, and you can see different datasets. Yeah, there are so many different datasets here. Then also there are so many pre-trained models. I think it's taking some time to load. Cool. So for I think the tokenization means split each text into words. Numericalization means convert each word into a number. Okay. Let me finish writing this. Lemmatization. So in this case, stemming and lemmatization means processing becomes process, something like this. Okay. So these are the pre-processing steps we usually follow in machine learning for text. But for deep learning, nowadays we just follow only two things. One is tokenization and numericalization, because those language models will take care of other things automatically. Cool. For pre-trained model, we are using this model, Deeperta v3 small. Think of this, it's very similar to what we did for image classification. We used ResNet model. So we used ResNet 1834. Similarly, for language models, we use Deeperta based models. Then this model was trained on particular way where all the words has its own embedding values. We need to use those embeddings values. For that, you can use this one, auto tokenizer from pre-trained. You just pass the model name it will download its own tokenization. Then you can ask to tokenize some words. So we used tokenization here. Then we are using tokenize function. Then you can pass any text like this. In this case, whenever start of the word, it uses underscore. Okay. And uncommon words will split into pieces. You can see it here. So here everything makes sense. But here you can see here play test is an ornithorhybus anatinus. So uncommon words are split, and the start of the word, it has underscore. Then we are using parallel for each row, so that it does not take a lot of time. Here you can see some of the row input and row input IDs. You can see it here. So for this row, this is the tokenized output. So in tokenization, you can ask, earlier I said there are two things. One is tokenization and numericalization. Here we can see you can see the numericalization, but here you can ask what is the numeric number value for some tokens. If you ask this underscore OF and it says 200. Transformer based models, the output label should be labels. So let's say in this case the output is score. We need to convert this to labels so that the model will automatically pick the label and input from here, and it does the modeling. Cool. Now let's talk about test and validation sets. So normally we mainly use two different datasets: training and validation. So let's assume you have got 100 different data points. Okay, and what you are doing is you are taking 80 data points and random 20 data points, and then you are using 80 to train a model and 20 to test your model. Okay, like test the performance. So this looks good, but the problem here is, let's say you are doing like 100 different models. 100 different models. In each model, you are doing different hyperparameters and different architectures, etc. And maybe out of those 100 different models, you are choosing the best model based on this validation data. So this is a slight form of overfitting, because you are trying so many different models and you are choosing the best one based on the validation dataset. Maybe it's a pure luck. We call this as overfitting to test dataset, validation dataset. Because you are trying like 100 or thousands of different model architectures, and you are choosing the best based on validation dataset, because each model is trained and based on the information of the validation data, you are progressing with other architectures. So there is a slight form of overfitting happens here. So the ideal way is split everything into 3 different types: training, validation, and test. For this problem, let's say there are 80 and 20. In this case, what we can do is we can take 70% for training and 15% for validation, then 15% for testing. So here you can use, you can build 100 different models using training data, and you can choose the best model based on validation data. Then finally, only at the end, try to use your test dataset to see how well it performed in your chosen model and report that results to papers and publish and other things. You can share that with others. Cool. So here what Jeremy is using is the problem statement comes with two different datasets, training and test, and Jeremy uses test dataset directly from here. He is not splitting from the training data, he just uses the test dataset from Kaggle. And validation dataset, this is the one we use from training dataset to choose the best models out of many different models. Let's say this is the function, and Jeremy adds some noises because to simulate real use cases, and you can see some noise here. So this is the original data we are going to predict. Then we are exploring different model options. This is just a 1 degree polynomial. 1 degree polynomial is just a line. This line does not represent the real underlying data set. So this is underfitting. Underfitting means this does not suit well for our data set. So still there is a room for learning something. So we can call this as underfitted model. Cool. And if you see this 10 degree polynomial, it learns so much. You try to match each data point closely. And this is very hard to identify because this is like it matches all the data points very closely, and we can call this as overfitted model, but it's hard to identify. How to identify this is you can use test data or validation data to see what's the difference between those two results. And here you can see the perfect fit. So the perfect fit is very close to the original fit, and here this is overfitting, and here the model didn't learn anything, so that's underfitting. And here the model learned so much that has the pattern only in the training data. It may not generalize very well, so that's why it's overfitted model. And here this looks like a perfect fit. Cool. So that's the concept of overfitting, underfitting, and right fit. Cool. I think we covered fine-tuning, ULMFit, overfitting, underfitting, train, validation, test bits. Now let's focus on other things. Okay, so here Jeremy uses the training dataset to create two different splits. One is training and other is test. Here in Huggingface they call this as test dataset, but originally this is like a validation dataset. You can see the validation set here is called test and not validate, so be careful. And also there is a very good blog post written by Rachel Thomas, and you can see it here, how and why to create a good validation set. I'll share this on our Slack channel. Maybe you can read this. It's a very good post. Okay, Tim's question, where is input set in DS? For example, DS1 input, this. Okay. So the input comes from our way of doing things. So this is the input, DF input, and this is a test. Let me read his question one more time. Where is input set in DS? DS has input, it's here. it is accessed using token function. The one we are passing is X, and you can see it here. The dataset has input, and if you are putting that into token function, then this function takes X input and it converts that to tokens, and it forms the input IDs. You can see the results here. So this is input, row equal to token DS. This is the first row, and you can see row input and row input IDs. So the row input IDs will be populated while doing this. So what are those IDs and where do they come from? The secret is that there is a list called vocab in tokenization, which contains a unique integer for every possible token string. We can look them up like this. For instance, to find the token ID of the word off, you can do that like this. I hope this answers your question. I see it was set in DF before going to this. Cool. Thanks, Tim. Okay. I think you can read this blog post. Did I share? Okay. Yes. Okay. For test dataset, we are directly using from Kaggle, and we are calling that as evaluation data frames. So it's a very similar approach that we did for training. We did the same tokenization and numericalization here. Then here Jeremy talks about metrics and other things. So there is a difference between metrics, loss functions. The loss function is the one we can take derivative and we can update weights and biases. Sometimes loss function and metrics can be same. For example, let's say you are trying to predict some price, house price, something like that. In that case, your metric is mean square error, and you can also use that as a loss function because we can take derivative of that. So, and that's the metric and loss function. Sometimes we cannot take any derivative, and we can use metrics to report something. It's for metrics is for humans, and loss function is for models and algorithms to update weights and biases. But sometimes it can be the same. Cool. And here I think that here the metric is Pearson Correlations. To understand Pearson Correlations, he has plotted different columns of housing datasets, and you can see it here. If they are in this direction, this slope, that means it's positively correlated. And in this case, they are, even though they are in good shape, it has lots of outliers. That's why the R square is, the Pearson correlation is low compared to the above one. Then once the outliers are removed, you can see the R value Pearson correlation increases. So Pearson correlation just tells you like how well the two columns are correlated. If it's close to 1 means they are very highly correlated. 0 means not at all correlated. -1 means strongly negatively correlated. And you can see the slope. Here the slope is slightly downward trend. That's why it's negative correlations. For our evaluation, we are creating correlations like this. We are using Pearson, and we are using correlation function, and we will pass the model predictions to it, and it will create this dictionary. Cool. Let me check. Okay. Now we are going to train model. I think we covered preprocessing. To train the model, we need a few things. I think it's very similar to what we have done in the previous sessions. To train image models, we did very similar things. So there is a batch size. Batch size tells you like how many input data you are trying to pass the model, and you will get some output. Based on the output, you update weights and biases. So that's the batch size. If you have a very good GPU, you can increase this batch size, and if you have got very limited GPUs, you can decrease the batch size. And epoch, this tells you how many times you are going to train, how many times you are going to show the data set to the model. So that depends on the epoch. Then learning rate. I think in Fastai we have learning rate finder. We can use that to find the perfect learning rate. But if there is no way to find learning rate, start with something slow, and then you can double the learning rate and see how it goes. Here you can see training arguments, something like learning rate and learning rate scheduler, like fit one cycle, those kind of things, and weight decay and other things. We'll learn this in our upcoming sessions. But for now, let's assume this is very similar to Fastai's learner, something like that. Then we have pre-trained model. Then this is our learner object. It has model arguments, then training data and test data set. Then here we have tokenization. This tokenization tells you how to convert words to numbers. Then this is the metric we are trying to optimize. Then we are training the model. Even with few epoch, we are getting like 83.4% as a correlation. Pearson correlation is very high for our model, which is quite good. Then this trainer object also has predict. In predict, you can pass the evaluation data sets and you can get the correlations. If you see the correlations, sometimes you can see something like greater than 1, but you know that correlation cannot be greater than 1 and it cannot be less than -1. So here what we can do is we can clip. So in our problem it's like 0 to 1, so that's why Jeremy clipped from 0 to 1. There was no negative correlations in our dataset. It's only not at all correlated and very highly correlated. And after clipping, you can see the results make sense. And I think he submitted this solution and he was at top 5%, something like that. I mean, even 1%. I can't recall now, but it was a very good solution. And a lot of people followed this approach and got into top 10. Cool. I think I'm going to end the session here. We covered how to train NLP based model, especially using Huggingface, and also we learned a few concepts like what is fine-tuning, and we learned what is ULMFit, and we learned the difference between overfitting and underfitting. Then we learned about what is the need for test dataset and what's the difference between validation and test. Then we learned the difference between metrics and losses. Then we learned Pearson correlations and clipping techniques. Cool. I'll see you next time. Thanks everyone.